So first of all, thank you for organizing this nice winter school and inviting us to talk about the links between mineral resources or raw materials and energy. Actually, it's a double link because we need raw materials and mineral resources to build the infrastructure of energy generation, energy storage, distribution and energy use, but we'll also need energy, of course, and a substantial amount of energy to produce this raw material. So this is the kind of things I will talk about in the first part of my talk, and then Cyril François will show us the interest of coupling or combining life cycle analysis databases with material intensity databases with input-output databases that account for the bilateral exchanges between countries in order to calculate an EROI. So it means you will have two talks in one, which is a very good example of efficiency. Okay, so on this figure, the different colors shows different activity sectors in the broad field of energy. For instance, in yellow, chemical elements which are used for the production and transport of electricity, in green for lightning, in deep blue for supraconductivity, etc. I won't detail everything. My point here is to show that almost all elements, chemical components of the periodic table, find a use in one of the numerous sectors of the energy. Of course, as I said, we need a lot of energy to produce these pure substances, to extract them from the natural environment, to purify them, and then finally to obtain pure metals, for instance. The most important part of the energy consumed at this end is used to produce these three metals: iron, copper, and aluminum. And if you add concrete, you have the four highest consumer of energy to be produced. 20% of the global energy consumed by the industry is used for the production of steel and cement. The production of iron, cement, and aluminum is responsible for the emission of about 50% of the carbon dioxide emitted from the industry. It's not that the production of iron and cement needs a lot of energy per ton, but as you see, 1 ton of CO2 is generated for 1 ton of produced cement, about 2 tons of CO2 per ton of produced steel, to be compared with 60 tons of CO2 generated for 1 ton of produced neodymium. But the amount of cement and iron which are produced every year is huge. 3.5 billion tons of cement, 1.5 billion tons of steel, 16 million tons of aluminum, and 20 tons of copper. Of course, these elements are also very important in the as I said previously, in the infrastructure of energy production, for instance. And if we want to address this question of how much energy is used or what is the energy payback of the infrastructure of energy production, we really have to focus on these four elements. But how much iron, aluminum, copper, and so on is used for the energy sector? Well, on this slide, this is the steel intensity in ton per megawatt for different kind of energy production facilities, starting from the left here to the right with the hydropower, nuclear, gas, coal, wind turbine, onshore, offshore, photovoltaic panel on roofs, in farm with a tracker to follow the sun. And we end up here with the CSP technology. So I have reported here 3 different sets of data, our own data, which have been taken mainly from the literature screening. The data which are listed in the Ecole database here in orange, and the data here, the cycles used by Erwich et al., who published a very nice and comprehensive study 2 years ago about this issue of how much raw materials we need for the generation of electricity. So basically what we see from very far away is that there is quite a good agreement between the different sets of data, except here for hydropower. So EROI et al. Used a very high intensity of steel, which is quite difficult to understand, but anyway. Again, I won't discuss that in very much in more details right now. We can do the same estimate for concrete here, for aluminum, and for copper. So there's a lot of points. It's difficult to really appreciate the discrepancy or consistency between the sets of data. I will illustrate this point later on. But again, if you look at these graphs at first glance and from very far away, we have the feeling that the amount of raw materials or the steel intensity in this case and the concrete intensity in this case, we have the feeling that we use more of these elements for the facilities producing electricity with renewable energy than in the power plants burning fossil fuels, which are here. Okay? Okay, so the basic idea now is to combine this material intensity with different energy scenarios in order to have an idea of how much concrete, how much steel we will need in the future to achieve and to follow the energy scenarios. So in order to account for this discrepancy in mineral intensity, in material intensity we find in the literature, I used two sets of data. So our own data, of course, which are shown here in black, and the data set from Houches et al. 2014, and we combine these two sets of material intensity with four energy scenarios for the next 20 to 40 years. We use two scenarios from the International Energy Agency, which are called 450, and new policies. So these scenarios runs until 2035. And then we also combine that with the WWF scenario, which runs until 2050. It's a very constraining scenario because in this scenario, 100% of the electricity is assumed to be produced with renewable energy in 2050. In order to achieve that, of course, the share of wind, solar energy, so you have the energy here. I'm not sure you can read, but it's the energy here as a function of time. So the share of the wind and solar energy increases significantly, whereas the hydroelectricity remains quite constant. Okay. So, and finally, the last scenario we used has been also published by the International Energy Agency. It's the scenario that has been used by Houches et al. It is called Blue Map. In this case, the increase of wind and solar energy with time is much lower, whereas the hydroelectricity is expected to have a more important increase than in the previous cases. Okay? Oui.
Here, the amount of energy is 10,000 terawatt-hour per year.
No.
Isn't it?
No.
To the right.
The sum or?
2050.
Some are.
Yeah, or even less.
Yeah.
Nowadays, it's already 20,000.
It's 22,000 right now.
In terawatt-hour per year?
Per year.
Electricity generated in the world.
Yeah, it's only for the renewable energy here.
But it's 100%
Yes,
renewable. So they assume that you divide by 2.
No. You have 10,000 of solar plus 10,000 of wind.
Exactly. Exactly. You have to sum it.
Plus 5,000 of solar.
Is it okay? Okay, so we will combine these four scenarios, as I said, with the two sets of material intensity. So I will very briefly show the results. So this is for concrete. This is a cumulative amount of concrete which will be sequestrated in the infrastructure of renewable energy production facilities, a cumulative material requirement. I insist on that, starting from 2010 until 2050. Okay, so in the case of concrete here, the blue symbols are for the blue map scenario, the green symbols are for the WWF scenarios, and the open symbols are for the scenarios new policies and 450. So basically what we see is that between 2010 and 2050, we will have to produce this amount of concrete here, which corresponds to 1 to 1.3 2010 world production, shown by this horizontal line. Is it clear for everybody? Yeah? Okay, so between 1 and 1.3 years of production. In the case of steel, the difference between the two scenarios is higher, but still we will have to produce between 0.8 and 2.7 2010 world production, and so on. Okay? So now if we compare with the results obtained with the material intensity for Erdrich, we get very different results for concrete here. The amount of concrete we will have to produce is much lower. Higher values for steel, quite similar values for aluminum, and much higher values for copper. The last point here for copper in 2050 for the WWF scenarios will be something like here. Okay? So, to summarize, in 2050, the cumulative amount of steel, aluminum, copper sequestrated in hydropower, wind, and solar facilities could be up to 9 times the global 2010 production. This is a huge amount, actually. And the energy required just to produce this pure substance, I mean the pure metal and cement, will be equivalent to 1.5 years of global crude oil production, 2012, which is also a huge amount. Well, in addition to base metals and concrete, as you know, the high-tech industries use a variety of what we call rare metals or critical elements. You call them as you want. In at least 3 sectors, the sectors of green energy production, in ICT, and in the sector of transport. So for the green energy production, you probably know that we have some rare earth elements, neodymium, but also dysprosium and praseodymium in the permanent magnets of the latest generations of wind turbines, gallium, indium, selenium, tellure in the multi-layer technologies of solar panels. I will not insist on that, but clearly these elements are used as vitamins in order to increase the efficiency of the production facilities, for instance. So for these elements, the situation is more worrying because recent studies have shown that until 2030, the yearly global demand in, for instance, gallium, indium, selenium, tellure, terbium, dysprosium, neodymium, and so on, just for PV cells and wind turbines should be boosted to 10 to 230% of the 2010 world supply, which is also really a matter of concern. Keeping in mind that for these elements, the room for improvement in terms of technology and use is much larger than in the case of base metals. You will never build 150 meters high wind turbine with bamboo or with whatever. It's very difficult to substitute base metals. It's probably easier to do that for these high-tech elements. Yeah, it means that every year you have to produce an additional amount corresponding to up to 200% of the 10%. To 10%, oh, sorry, should be boosted to 10%, also between 10 and 230% of the 2010 world production. It depends. This is what you see on this graph, actually. This is the additional amount you have to produce in percentage for the different elements. So the 10% is for praseodymium, and 230% is for indium. Okay?
And this means 2030, price in one case, then 10% more than 2010.
Yeah.
Okay, not every year.
So yeah, every year. No, it's not an increase per year. It's every year you have to produce this additional amount, which is between 10 to 30 and 230% of the 2010 production. Is it okay? So in terms of energy requirement, of course, it has nothing to do with the previous base metals and cement, because the amount of these elements which are produced every year are quite low. But still, it's a matter of concern. So these estimates are probably optimistic because, first, the installed capacity that we use to make the estimate was calculated directly using the average expected energy production, which is listed in the scenario. So we did not use an overcapacity, okay? The second reason is that some material-intensive technologies are developing. Just an example here, the wind float project, which proposes to put these wind turbines on floating platform that can be put away from the coastline to have better wind conditions. The platform itself contains 1,500 tons of steel. So clearly, you double, in this case, the steel intensity in tons per megawatt capacity.
How about chrome?
Sorry?
Put in the ocean, you need chrome.
Yeah, you need, yeah, you need chrome. That's true. So I did not consider that here, but you need a bunch of of elements. Chrome is one of them. So another reason is that we really restricted our study to a small part of the energy pathway. Actually, just the production of electricity with turbine and photovoltaics and passive solar and also hydropower. We need also raw materials for the delivery of electricity, for the storage of electricity, for the use of electricity. This is clearly not included in our estimates. What about recycling? Until now, I just talked about the need of raw materials or mineral resources. But in contrary to oil, metals can be recycled, of course. Well, not before 30 years, because it's the average lifetime of the infrastructure of renewable energy we are building, and not for all chemical elements. Here you have the recycling rate in blue. For the recycling rate is higher than 50%, between 25 and 50% in green, and so on. And you see that even copper has a recycling rate lower than 50%. At the global scale, it's about 30%, actually. And this is the best cases. But for many other elements, like lithium or gallium, indium, and so on, it's very difficult to extract them. Yeah.
It's what we do today, or is what is feasible as recycling?
Well, you know, in my laboratory, I am in laboratory for geochemistry. They extract rare earth elements every day. They have a column and it's feasible, but it doesn't mean that it will be done because it has a cost. It's technically difficult. So if you want to produce a mass of products, you cannot use the same techniques. It's feasible, but it will be difficult to.
It's just not feasible to recycle.
Yeah, you are right. and this is what I wanted to say here on this slide. In some cases, the limits of recycling can be technical. There is a thermodynamic limit, of course, if you want to recover elements in minute amounts, dispersed in a matrix, and so on. And you know that since several years, we try to produce very complex materials which have particular which are light, for example, and very robust, so it's useful for the planes, and this kind of alloy are very difficult to reuse then after they are recycled for the same use than they were made for. Okay, recycling, another limit is the price of the primary resource. You are probably aware that in 2012, Solvay opened 2 plants in France to recycle some rare earth elements. So it was lanthanum, cerium, terbium, yttrium, europium, and gadolinium. So they were very proud, and they say that that was a good example of the tangible contribution of Solvay as a chemical manufacturer to sustainable development. Well, actually, 4 years later, Solvay closed the recycling plants, and mainly because the cost of production is now too high at the current price of primary rare earth production. The same problem occurs also for steel. Right now, the primary iron from China is competitive compared to European recycled steel. So it means that the people who are working to recycle steel are really in bad shape right now. Okay, so now a few words about the energy intensity of mineral resource production. A common observation is that since this is the example of copper, the copper ore grade in average decreased significantly since 1900 to today. In 1900, the average grade was about 3%. Nowadays, we exploit deposits which are very poor in copper. The average copper grade is 1% or even less. This has 2 implications. The first one is that it increases the reserves mechanically, because when you decrease the grade, the ore grade, you have access to a more important volume of rocks containing copper in lower amount, okay? But still, you increase the reserves. And in 19, the total copper reserves were estimated to be 25 million tons. Right now, they are about 750 million tons of copper. So the reserve increase while we decrease the concentration or the ore grade of copper deposits. The second implication, of course, is that you need more energy to extract copper, to produce copper from low-grade deposits than from high-grade deposits. The red curve here shows an estimate published by Chapman in 1974. So the amount of energy you need to extract copper when you lower the ore head grade. Actually, today we are on the red square, which means that things are never simple. In the meantime, the industry was able to improve the efficiency of the copper production, and so we don't follow this line. But in general, we have to wonder what will happen when we will extract copper from deposits with a grade lower than 0.5. Yeah.
The 1.5 billion barrels or tons or whatever, or no, the 1.5 year of oil production of energy embodied into the materials to build is at present ore grade, or it includes a decrease of the ore grade?
It includes, yeah. I did, I consider that in 2050 the ore grade was lower than 0.5. Okay, but honestly, I'm not sure that, so we have to do the calculation again. It's really a preliminary result. Another example of this improvement of the industry efficiency, the amount of energy we needed to extract 1 kilo of, to produce, 1 kilo of steel in 1950 was about 60 megajoule. Now it's lower than 20 megajoule. Okay, so this is a very general result. However, things are still not that simple because in the meantime, we develop new kinds of steel for new applications. And actually, the steel used for the automotive industry has a particular composition, and it requires about 50 megajoule per kilogram to be produced. Some technical stainless steel have an energy intensity up to 300 megajoule per kilogram. So it's very difficult to have a very general view of the problem. So to summarize, the energy required for primary production of metal increases with lowering the head grade, but this is partly balanced by technological improvement. It's important to realize that the type of energy which is used to produce these metals is country dependent. The energy required to produce secondary, so to recycle metal, is much lower than for primary production. The recycling rate changes with time, and this depends on the price of the primary metal. Again, the recycling is country dependent. And the last point, the energy required for energy production varies with time, of course, and is technology dependent again, and it's country dependent again. So if we want to address all these points, what we need is a dynamic modeling with a change that accounts for all these changes with time. And we also need somehow to account for the geography, I mean the location where the raw materials and the mineral substances are produced. So this is what Cyril will talk about in a few minutes. I will just say a few words about the dynamic modeling. So I think I belong to the first school you mentioned a few minutes ago, Gael. So we used dynamic modeling, so a so-called predator model, which describe the interactions between a prey and a predator when they play together. So to make it short, in our example, the prey is the resource. And I have worked on copper because there was a lot of historical data available, so we could constrain the model. Okay, so the prey will be the reserve of copper, which varies with time as a function of the amount of the amount of copper in the reserve at time t times a coefficient here which corresponds to the reserve regeneration. So this might appear to be a bit strange at first glance because we are talking about fossil resources. But as I said previously, the reserve increased indeed with time. Okay? Then the production of metal is a function of the reserve, but also of the prey, and the prey of the predator. Sorry, and the predator in our case is the wealth. So it included a lot of things: capital, infrastructure, labor, information, as also a value, and these kind of things. The evolution of wealth. Again, is a function of the resource, of the wealth, of the stock of wealth at time t. And we have two other parameters here corresponding to the creation of wealth and the erosion of wealth, wages, erosion of capital, and so on. We can show that the ratio of delta to beta is proportional to price, which is very interesting because we can use now, and we can decide that the regeneration will also be a function of price. If the price is high, the benefits are high, the industry can invest in exploration, increases its chances to find new deposits, and so on. Okay? So graphically, the two equations I showed on the previous slide can be represented like that. So we have a stock of reserve a flow-in here corresponding to the discoveries and the decrease of the ore grade, a production of copper, a flow-out, the same for the wealth. Then the primary copper which is produced is incorporated in goods, okay? These goods, after a certain amount of time, which is about 25 years for copper, becomes waste. And they feed a second stock here, which is the end-of-life product. This stock can be used as, in the case of primary extraction, as a reserve to produce recycled copper, okay? And then, again, you have a back loop here. The product, after 25 years, can feed again this stock of end-of-life product. At each loop here, there is a loss of copper corresponding to the recycling rate. Okay, so we have 7 parameters to constrain, and we have a lot of historical data. So I won't detail that, of course, but in yellow here you have the historical data, and in black this is the result of the model. So the production from 1900 to today, the evolution of reserve, the evolution of price, the evolution of the production cost. So here we have 2 sets of historical data. The evolution of the revenue from the mining and the mineral processing industry, and the profits. This is for the primary production. For the secondary production here, we use data from Gloser et al. We published a very nice paper. This is a mass flow analysis at the global scale, and they were able to estimate the evolution of the stock in use, so the stock of copper in the anthroposphere as a function of time, the stock of lost copper, and the flow of copper toward the end-of-life stock, okay? So again, in blue, we have the historical data, and in black, these are the results of the model. So I have to hurry up. So this is the evolution of the different parameters of the model, okay? And now we are here. So this is the production curve in blue. This is the evolution of price in pink, and the profits of the mining industry in yellow. So what happens if we keep the values of this parameter constant, and we let the model evolve until 2100? We observe a peak of production, which is a classical bell-shaped curve, well known from people using logistic approaches to calculate either peak oils or copper peak, or peak copper, or whatever. This occurs in 2035, and at the peak, the production of copper should be about 30 million tons per year, which is in good agreement with what has been published 2 years ago by Nofre et al. Using a logistic approach coupled with an evolution of the demand. Okay, so now we can also change, for instance, the price of copper. We can think that at this stage, if the demand is still growing, the production decreases, the price will increase. So we just need to increase this delta components, the price increases. And as you see, the benefit of the profits of the mineral industry shows 2 peaks here, which allows one to produce a bit more copper and to have this asymmetric shape of the production curve. Okay, these are just examples. Actually, you have plenty of scenarios you can think of. So getting back to the amount of copper we need to produce with the WWF scenarios for the renewable energy, we have to produce this amount of copper, okay? Which means that we have to increase the production of copper between 2010 and 2050 along this green line. You see that this increase of production is exactly the increase of production we observed between 1970 and 2000, when the countries which are actually developed, currently developed, had finished to build the infrastructure. So we can imagine that in a world without developing countries putting up the production, we should have this kind of increase in production. This is exactly the production we see just for the renewable energy, so to build the infrastructure structure of renewable energy. I think I will stop here because I have no voice anymore, and we need some time for 5 minutes, and then Cyril can also have time. Yeah. Wait a minute. I don't know. Where am I? Yeah, I was here. So the last thing, no, it's important. Actually, it's important. Yeah. It's the last message. So this is the primary production of copper, but as I mentioned before, we can also calculate what the recycling should be. And what we predict is that the amount of recycled copper will increase significantly after 2040. Why? Because in order to recycle, in order to produce secondary copper, we need a stock of end-of-life products in mass, which can be accessible at one time. And this will be possible after 2040. And actually, we are on this. We are here at the moment. So, and eventually, the secondary production will be higher than the primary production after, well, 2040 or 2050, something like that. Which means that if we add the primary and secondary production, we should stay quite high in production at about 40 million tons per year until 2090, which is a good news. Now, the second interest of this kind of calculation is that we know the proportion of primary and secondary copper in the total production. And since the energy needed to produce secondary and primary copper is not the same, we can finally calculate the total energy which is required to produce copper. In that case, we see that, of course, the peak of energy occurs at the peak of the primary production, and after that there is a really a strong decrease in the energy used to produce copper. The bad news is that we are trying to make the energy transition over a period of time where the energy, at least for copper, to produce copper is very high. It should be better to have done it here or to postpone maybe a bit the transition, just on this criteria, of course. That's it. Thank you.